Okay. Hi everyone, and thanks for being here. So my name is Junaid Majeed, and I am going to present my work on electronic transport in superconducting wires, which I've been doing with Abhishek from past few months. So before going to the title, let's first take a look at Kitaev chains, what Kitaev chains are. So this is the Hamiltonian of the Kitaev chains. So Kitaev chains, AJ and AJ dagger are the creation and annihilation operators for the site J. And there are two kinds of terms basically. There are hopping terms, which are of the form A dagger A, and there are superconducting BCS type of terms in Kitaev chains. And this delta in the superconducting parameter it's a free parameter. It's not calculated self-consistently as in BCS. One may think of this as a quantum wire which is embedded on a superconducting substrate, and this delta is coming from the induced superconductivity from this substrate. Now, why are Kitaev chains important, and why should we study its transfer properties? Now, Kitaev's model, this is the simplest model for realizing Majorana bound states, MBS. What are MBS? So MBS are zero energy bound states which are localized at the ends of the chain, and these provide a way to construct decoherence protected degrees of freedom, which are essential for building a reliable quantum memory. Now, these are also the candidates for realizing Majorana fermions in physical systems. Now, in the previous Hamiltonian, there are Majorana bound states present only. These bound states are present only in certain domains of certain parameter regimes of the Hamiltonian. For this Hamiltonian, it is when 2 eta s means the hopping parameter is greater than mu s. Okay, and of course delta should be non-zero. Otherwise, it's just a tight binding metal. Now, transfer properties of Kitaev chains. Now, it's important to have experimental signatures of these bound states, and the transfer properties of Kitaev wires, they help in establishing those experimental signatures. Now, let me give a brief overview of what we did. So we considered a system where you have a wire, as you can see the red line, and we coupled this wire with the two thermal reservoirs, and the thermal reservoirs are pure metals, and as you can see, HWL and HWR are hopping Hamiltonians from the wire to the respective reservoirs. So there is this left bath and right bath. Okay. Now let's say in this system we start from a state. Before telling you exactly what we did, let us intuitively see what we are trying to look at. So let's say we start from an initial state in this system, and the initial state are the baths are at some temperatures beta L and beta R. Oh, sorry, there should be an L here. Beta L and beta R, and the system is empty, means it's in vacuum state. Okay. So what we expect to what do we expect to happen? What we expect to happen is that as you let the system go at t equal to 0, the electrons will diffuse from one bath to another through the wire. So it will constitute a current in the wire. Okay. So if you have finite baths, then this will roughly be the profile if there exists a steady state. Okay. I will discuss this steady state, when does it exist, but not in full detail. So if there exists a steady state, then the current initially will increase. First we will have the first red line is the transient state. Then you will have a steady state, and then after everything has equilibrated for finite baths, then you will have this green portion, which is the equilibrium. Now, obviously, when you increase the bath size, this time for equilibration will increase and will go to infinity for infinite baths. Okay. Now, we are interested in this steady state bit, and what we have done is we have calculated. We derived an analytical expression for the value of the current in this steady state. Okay. Now let's take a look at the Hamiltonians we took for the calculation. Now the Hamiltonian, obviously it has 5 parts. So first is the wire. As you can see, we took a general Hamiltonian which contained arbitrary long range couplings, means not just nearest neighbor things. And there are also every side of the wire is coupled to the left bath as well as right bath, as indicated by HWL and HWR terms, and the baths are simply normal metals, the tight binding metals that you can see. And below you can see these are these are creation and annihilation operators. Okay. Now, okay. Now to calculate the current, now in quantum mechanics, what we do, we need physical observables, right? We need operators. So how is current defined in these kind of systems, right? So the way the current is defined is you take the number operator at any site and take its derivative, okay? Then use Heisenberg equation of motion. So it is, I mean, if the current is conserved in the system, then it will come in continuity form, and you basically identify the current from there. So for our system, you can do it in the bath side, because in the bath side the current will be conserved, not inside, because inside there are non-number preserving terms. Okay, so you can do it there, and you will find that this is the expression for the current. So all we needed to do was solve the Heisenberg equation of motion for the system, okay, and then obtain the current by this formula, okay. Now let's look at the Heisenberg equations of motion. Now, so this CL is the system, is the Heisenberg equation of motion for the system operator CL dot. First, second, and third are the Heisenberg equation of motion for the bath on the left and the right. So primes are the right, okay. Okay, fine. So now, was it possible to do so? Yes, and the answer is yes. So you take these two Green's function 11 and 12. These Green functions are for the bath or for the bath operators, okay, and L and R you can basically associate, okay. So the third term is treated as the inhomogeneous term, and you can write down the solution for the bath operators, okay, and then you take those bath operators and plug them into equation 8 and take a Fourier transform. So you will eventually get an expression for CL of t, okay, as a linear, as a Fourier transform integral, okay. So now then you can basically calculate the current, and this is the expression for the current you get. Okay, it's too long. Okay, so and all the traces contain matrices, and all these matrices are functions of the matrices which were involved in the Hamiltonian. So these H, delta, V, HL, all the matrices in the trace are basically in terms of those. You can see it. And K is delta minus delta transpose. Sorry for not mentioning it earlier. So K is delta minus delta transpose. It's also a matrix. So this is the result. So, but there were certain things about this result which made us a bit skeptical about this. So first thing, the expression of the current was not symmetric with respect to L and R. So, so this was current calculated at the left end, okay. So the current calculated at the right end would be symmetric. You just replace L by R, okay. The calculations would be similar. So we found that the expression is not symmetric with respect to L and R. It means the current going in from the left end is not the current leaving from the right end. So, and also if mu L was equal to mu R and beta L was equal to beta R, means that initially there was, you start with a symmetric situation. The current was not zero. This expression does not necessarily give you zero, okay. Now this made us skeptical about this result, and we resorted to numerics. So for numerics, we took a nearest neighbor coupling, a simplified version of the Abel Hamiltonian. You take nearest neighbor coupling. A's are system operators, BLs are left bath operators, BR are right bath operators, okay. And only one side of the system is coupled to the bath. Means basically the end side of one wire is coupled to the first side of the bath from here, and likewise from the other end. Now we ran numerics for the system, and from the numerical simulation, we found that indeed this expression is correct, because the steady state that we obtained, these are the parameters, it matches with the new simulation, okay. And the initial state was chosen to be the same which I mentioned earlier, completely empty system, and the baths to be in thermal states, okay. Now, so this is for delta 0.25. Now then, with the simulations at our hand and some analytical expression, we looked into other things, and the other thing that we looked at is, when does this steady state exist? What exists? So far what we have found is, if you keep all other hopping parameters to be 1, the hopping parameters are C dagger C coefficients, and you vary delta. Okay, this is from the simulations, 100 bath sites on both ends. You find that for delta less than 1, you have a steady state. For delta equal to 1 is the exact breaking point, and for delta greater than 1, you don't have a steady state. Means, as you can see from the plots. Okay, so this is one thing that we are currently looking at, and we are trying to. I mean, we want to eventually obtain a relation. I mean, obtain the boundary equation for which separates the steady state and non-steady state domains. And there's one more thing that we looked at was the variation of this current with respect to the number of sites in the system. Earlier, all the plots were the number of sites in the system were 2, and this is from the simulations. Okay, and this is from the analytical expression. So we found out the current does not go on keep on increasing; it saturates to some value. Okay, and this result also we are trying to explain, and we are also trying to look at the system from different perspective, from scattering perspective to be exactly, and trying to compare the results from that with the results here. Okay, this is it. Thank you.
Questions?
Current, this is this one. Current was N. Okay.
When did you measure this?
This is current. I mean, this is the steady state current. So no, there is no time involved. This is from this. This is from this expression. You have these traces, and traces will involve dimensions, and those dimensions will be given by the number of sites you take in the system.
And you said that from this expression, it was not evident that for mu L equal to mu r and TL equal to TR, it's 0.
Yeah.
When you computed numerically, it's 0. So what was wrong?
No. What, that I didn't say. I just said that even if you calculate numerically, you don't get 0. I'm saying the numerical simulation matches with this expression.
Okay. But then even with when
Uh-huh.
then you don't get 0 current.
I mean, apparently you don't. I mean,
what's the reason for that?
Yeah, I don't have any answer for that yet. That is true, but still, so one of the reasons is this is a really weird system. I mean, you have these particle numbers don't conserve, so maybe that is the reason. So, but still, I mean, for the symmetry case, I mean,
the particle numbers are conserved in the baths.
In the baths they are conserved. In the wire they are not conserved. So that is, I mean, probably the answer. The particle numbers within the system is not conserved.
And you didn't look at the energy current.
Energy current, of course we look at, and energy current was conserved. We didn't plot it, but we found out it is conserved. So energy current does not have this problem.
Hello. So if you can, is there a thing that you can do to the right bath that makes the current 0, steady state current 0? Like maybe it doesn't become 0.
Yeah, there is one thing you can do. First, there is a particular configuration of these mu L, mu R, TL, TR, which will give you the current going in from the left end and the current going out from the right end to be same, which is you take mu L equal to mu R equal to minus mu. Okay, then the expression you get, this expression reduced to integration over d omega and some trace and f L minus fr at of course omega mu and mu t and minus mu t. So equal temperatures and mu's you can from there you can see the current will go to 0 if temperatures are same and mu is 0. This has been verified numerically as well as from this expression. Yes.
There's some asymmetry in the current flow, but what determines the direction? Do you see that? Like,
so so that the direction. I mean, it's. I mean that I don't have an exact answer what determines the direction, but this. I mean this equation determines the direction. And that's the only thing I can say.
like
because
do you see what can you change in the initial condition or something which reverses the direction? I mean, just.
Oh no, that I didn't look at. There's one thing, one way to think about this non-homogeneous current within the wire is that this wire is supported on a superconducting substrate. Okay, yeah. So that substrate acts as an electron reservoir. So it is fine to have the currents coming and going different. Yeah.
You said the current is sorry, yeah. The current is sub-diffusive. No, sorry, you said diffusive. The
No.
charge.
I just said
transport is
that. I
diffusive.
just said from intuitively if you okay, where did that go? I just wanted to give a rough intuition that if you start from empty system and you place your baths at some temperatures and then you let that system go, then these electrons will go through the wire. They will diffuse through the wire to the other end. Okay, and that will constitute a current.
Kind of, you are losing some charge inside the wire.
Yeah, this charge,
So-
so you lose some charge in the, because inside the wire the number is not preserved, and
No, that's fine. I'm just asking why do you call this diffusive? Because you are losing some.
I just wanted to say, okay, fine, maybe diffusive was a misleading term, but I just wanted to say this electrons will flow from one end to another.
I have a small question, one more question. The energy current, the steady state energy current versus N, how does it behave with N?
Okay, that I have not looked at yet. Sorry. Okay, I'll look at that. I mean, possibly.
Now we would like to thank the speaker